name is Kat Villamo. Some of you already know that, those who attended the Wednesday's lecture. So I can greet you in several languages if it's the language that you natively speak. So you just raise your hand so we get to know who is coming from which part of the world. Okay, let's start with hello. Who speaks English natively? Okay. Ni hao. Oh, many more actually. Konnichiwa. Oh, some people from Japan. Hola. No one speaks, there is someone who speaks Spanish. Namaste. Namaste, okay. Salam. Shalom. Привет. Vitam. Guten Tag. So if I did not name your language, can you raise your hand and just greet us in your language? Yes? From where? Vietnam. Oh, yeah, I don't know how to say hi in Vietnamese actually, so it's something to learn. Anyone else? No? No one else? Okay. So typically the first 5 minutes are spent on some semi-random facts of the day, so you can use some of this knowledge in your trivia or whatever. So what happened on this day in history? So today is July 26. In 1509, the Emperor Krishnadeva Raya ascended to the throne, marking the beginning of the regeneration of the Vijayanagara Empire. So who knows where it was happening? What is the contemporary country that is currently occupies the space of the empire? Where? Yeah, correct. India. You can guess it by the names. So in 1745, the first recorded women's cricket match took place near Guildford, England. In 1803, the Surrey Iron Railway, arguably the world's first public railway, opened in South London, United Kingdom. In 1887, publication of the Unio Libro founded the Esperanto movement. Who have ever heard of Esperanto? Okay, so what is Esperanto?
It's like supposed to be like the international language.
Yeah, sort of like international. It's constructed language. It was designed. And was designed on the basis of Romance languages. So if you speak any Romance language like Spanish or French, it would be very easy for you to communicate in Esperanto with other people and very easy to learn. So what other constructed languages exist? Do you know any? Like Clinton? Yeah, or Dothraki from the Game of Thrones. Okay, in 1951, Walt Disney's 13th animated film, Alice in Wonderland, premiered in London, England. And finally, in 2016, Solar Impulse 2 became the first solar-powered aircraft to circumnavigate the Earth. So some semi-random facts. Now, let's try to recap what have you learned so far. So what is this subject all about? What will you learn in that subject? Any guesses? Raise your hand. What sort of skills you will acquire? Yes? Programming. So what it means, programming, it's very general. So what sort of skills will you get from this? Write in Python. So you learn the syntax, so you learn how to speak Python language. What else? It's the very tip of the iceberg to just learn how to speak that language. You also need to think in that language, right? So you need to rewire your brain to think like through all the steps explicitly. What else?
Say problem-solving skills.
Yeah, this is the most difficult one. So if you can learn like a programming language itself very like easily within 1-2 weeks, this problem-solving skills is much harder. So it takes a lot of time, it takes a lot of practice. That's why you have wonderful Grok worksheets. So whenever we have end of subject survey, so the most positive feedback we get is for Grok. And this is where you will spend most of your time, in addition to tutorials and lectures, of course. So But still, so programming is just not a single skill, it's an art. So, and why it's an art? So who can recognize this person? Who knows this person? So this person wrote a book, or like 3 books, magnum opus, The Art of Computer Programming. His name is Donald Knuth. Who have ever heard of this person before? He is actually the person who developed this particular tool where I make my slides. That's how the slides look like. So you see, it also looks like code, right? It's called LaTeX. So Donald Knuth described the most basic and advanced algorithms in his magnum opus called The Art of Computer Programming. And he says, computer programming is an art because it applies accumulated knowledge to the world, because it requires skills and ingenuity, and especially because it produces objects of beauty. A programmer who subconsciously views him or herself as an artist will enjoy what he or she does and will do it better. He is also called the Yoda of Silicon Valley. Lex Friedman has a very nice interview with him, 3 hours of constant joy. He also coined this term geek. Who has ever heard of this term before? Yeah? So what is geek?
Someone who's really interested in something specific.
Yeah, when you typically think of like computer scientists, you think of this like geekness in it. And he said like Alan Turing was the #1 geek in the world, the very first one. And what are the main characteristics of a geek person? So, and he coined these 2 major characteristics, jumping between different levels of abstraction, and the second one is addressing non-uniformity. You need to think about all the corner cases, considering all the cases. So when you program, you to some extent model the world, right? So, for instance, when you think about different types of programs, even the LMS, the Learning Management System, is a program, right? It has some database of students, their lecturers, their subject coordinators. It has the web interface, some interaction between the 2. And it models the way the university lives, right? So what are these entities in the university? So there are entities such as students, there are lecturers, there are subjects in the university, there are exams, right? And you need to decide, kind of make this abstraction. What is the abstract entity of student? What properties does student have? Can you name some properties of a student? If you want to describe not a particular student, but an abstract general entity of a student, what would be these characteristics of a student? What all students have in common? Studying, okay, they have the activity called studying. They are studying particular subjects, so they are enrolling into the subjects. They also get marked in particular subjects. But students also have their student ID, their first name, last name, date of birth, etc., right? There are some properties that are common for all students, right? And there are some activities that are common for all students. So in order to make these conclusions, you need to make some generalizations, right? You need to think about on different abstract levels. So, and in terms of considering all the cases, think about this typical problem called linear search. Who heard of this problem before? What it means, linear search? Yes, there? So yeah, you have some list of numbers. It might be unsorted. Usually it's unsorted, right? And you need to find a particular number in this list, or say there is no such number in the list. when you think about this problem and the way you approach this, you need to think about all these corner cases. For instance, what happens if the number is basically the first number you see in the list, if you go one by one, element by element, you go through the list, and actually the first element you see is the element you're looking for. This is the best case, right? You just need to perform one operation. You just check whether this is the correct number you're looking for or it's incorrect. What is the worst case in this? Like you have, suppose, like millions of numbers. There's like a list of millions of numbers. You're looking for a particular number. What is the worst case scenario? The worst case is just there is no such number in the list, right? You have to go through the whole list. So you, like, if you do this one by one, element by element, you will have to perform million of comparisons. Or also the worst case is like you see this number at the very end of the list, right? On average, you will see it somewhere in the middle, right? So you need to think about all these corner cases. When you develop an algorithm, you need to think about what is the best case scenario, average case, and the worst case scenario. You also need to think about the user. What does the user provide to you? Maybe the user will not provide the number, they will provide some like hello world string. How your program will respond to that. So this is what I mean by considering all corner cases. And these skills take time to develop, a lot of practice. So you need to program and program and program to develop these skills. So you need to learn how to conceptualize a problem, right? So you have some real world scenario, and then you modeling this using your program. So you need to do this, identify the core concepts and how they interact. Then you need to identify different modules. Like in the LMS, there is one module which is like the university with its subjects, another one is the student, another one is like the life of all subject coordinators and lecturers. So you need to identify those modules and how they interact. And finally, you need to formalize it. So, and the core aspects that we need to learn, first, you need to learn the syntax of that language. You need to learn how to express your thoughts in that particular programming language. In Python, it's a high-level language, so it's relatively straightforward. It's very close to natural language, but there is a very important distinction between programming languages and human languages. What is that? What do you think? What is the major difference? In human languages, there is a lot of ambiguity that is resolved in this particular context, in this particular situation. For instance, the word book can be used as like I read a book and I book a flight, right? There are different meanings. In programming languages, there should not be any ambiguity. There is only particular meaning, the particular interpretation that you use. So, and when you learn this programming languages, you learn this particular syntax and grammar of that languages. So, but it's only, as I said, the tip of the iceberg. So, in addition to that, there are a bunch of algorithms, how to search for number in a list of numbers, how to sort a list of numbers, and there are like a bunch of data structures that people find useful for different scenarios, like trees, queues, stacks, etc. So, and each algorithm, most of the algorithms can be implemented on different languages. You can see like the merge sort algorithm implemented in Python, C, C++, etc. So this is the next level. So you first learn how to speak the language, and then you also learn, in addition to that, you learn how to develop algorithms, how to use algorithms, for which scenarios you need to use this particular data structure. There are tons of books, and Donald Knuth is the best one, The Art of Computer Programming. So, and those books typically use pseudocode, like abstract representation of programs, not particular programming language, because people speak different languages, different programming languages. So if you implemented your algorithm in Python and some other person speaks C or C++, it's much easier for them to comprehend this code as pseudocode, not in Python. And that's why all the books they typically use pseudocode. So, and of course, there's a lot of accumulated knowledge already. And this knowledge and this like typical algorithms such as quicksort or merge sort, they are collected in libraries. So you do not have to do everything from scratch, reinvent the bikes, right? You just load the library and you just say, okay, qsort, whatever the list. So you just apply this particular function and you get the result. You do not need to re-implement this, right? It's a common solution. And there are frameworks. So frameworks are more general. So they're kind of collection of libraries that are used for particular purposes. For instance, Django is a framework in Python for developing web applications. A whole bunch of libraries that are useful for developing web applications. So in Python, it's very nice, actually, language in the sense it's not only open source, and it's constantly updated, but it also has a very rich library collection. So if you do scientific calculations, you can use SciPy. If you do data analysis, you just load a bunch of useful functions and methods from pandas. If you do machine learning, you load TensorFlow. You can also play with large language models using the Hugging Face library. So there are many, many different libraries in Python. As soon as you learn it, you can just reuse these libraries and just for your own problems. On top of that, we also have some skills and practice. How to refactor the code and how to write a good code from the first instance. But it's only coming after lots of programming experience. And of course, you are not isolated. Typically, if you are not a PhD or if you are not working on your own project like in this subject, so typically people collaborate or they work in some company on a joint project. So, and they typically work on a particular module, right? So your module interacts with some other modules, and you need to understand, for instance, not only your module, but its interaction with the whole system. So there are different roles in the company. If you join a company as a software developer, you may also then become some system architecture or do some other roles. So team management, team lead, or team project management. So there are a bunch of other skills you need to acquire on top of that. And finally, since we all collaborate, we use these collaborative tools such as GitHub and SVN. So we can work on the same project together without any conflict. So if I edited code, someone else edited code, and now we're trying to merge it, there is a conflict, what to do? So we make sure that it all goes smoothly using all these collaborative tools. So, and in this subject, we will typically mainly focus on syntax and basic algorithms, right? So this is very introductory subject. And we'll also mention some libraries, the most common ones. Okay, and a bit of geek advice to you. If you want to know this, like get sense of the geek world, I very much recommend you reading Cryptonomicon. 1,000 pages long, but it's still like, it's very nice. It has really nice mentions of these problems that we touch on in this particular subject about computability, Alan Turing, and the development of the whole field. So we put the PDF on the LMS, I believe, so yeah, feel free to read it. Now, to this particular lecture agenda. So we will start with more like theoretical discussion, more philosophical discussion. And it's not examined. Relax, take it easy. And then we'll proceed to some basic examples of Grok usage and how to do your worksheet number 0. You already discussed with Shannon some basic programs, right? So a program is sort of like a sequence of steps. What matters is that there is a sequence, it's ordered set of steps. And determine what the steps should be requires learning how to computer think in quotes, because they don't think. There's a particular set of steps that are provided by computer programmer. Even in the large language models, it's just a program. So computers do not think, and they do not really understand. It's just whatever you provided, they perform exactly that. Okay. And at the most basic level, a program is made up of a sequence of so-called statements. So each step is called a statement. It's a basic step, basic operation. And this program runs sequentially, right? You start from the very first step, the first statement, and you go like one by one till you finish the final one. So here is an example of a simple program for visiting a friend's house. So in the program, there is always some initial state, right? So initial date or initial state. So our initial state here, we assume we are in our particular location. And our desired state, so there is also desired state where you want to get after your program runs, right? So our desired state is to be in this friend's house. And now we have the set of steps. You see that there are discrete steps to get from the initial state to the desired state. So what we need to do, for instance, head south on the Peninsula Freeway. Then the next step, take the Red Hill exit. The next step, keep taking the left turn, at each intersection until you cross the bridge. Then, if you reach the beach, turn around and go back, you've gone too far. And finally, park at the Red Hill Bakery. So from this program, what you observe is there are some basic characteristics that you can notice. So first, as we mentioned, there is like a sequence of steps. And we start from the initial state, and we expect to finish at some point. So those are the major characteristics of the concept that we will introduce. This is the major concept in programming that we'll introduce in a few minutes. And in order to introduce the concept, I would like you to try to guess this person. This person is directly related to the concept. Any guesses? Any guess? No guesses? Okay. Of course, it is Muhammad ibn Musa al-Khwarizmi. Now, try to guess how this person is related to our subject. Sorry? What is the relation between this person and our subject? And the concept that I'm trying to introduce in a few minutes. So if you look at this, al-Khwarizmi, does it remind you of something? Yeah, of course, it's algorithm. It's the person after whom we have this name, the word algorithm. He was the author of the Compedia's book on calculation by completion and balancing, Al-Kitab al-Mukhtasar fi Hisab al-Jabr wal-Muqabala, written in the 9th century. So the book described a positional decimal number system invented in India. Why decimal? Why do you think it's a common system? It's the most common number system in the world. Why? Because we have 10 fingers. People just count by fingers. And there are other systems that are based on 5 and 20. So, but of course, computers do not use decimal system, they use binary system, right? So we need to adjust to binary system as well. And the book, in addition, introduced this notion of zero or cipher, or it's also related to the word cipher. And then in the 12th century, it was eventually translated into Latin as algorithmi de numero indorum. So that's how we get the word algorithm. And if you look at the name of this book, you can also spot another contemporary concept. Can you guess another one? There is a corresponding word. Which one? Algebra, it's algebra. So everything that starts with al comes from Arabic. So, okay, as I mentioned, we have this word algorithm named after the person. So what is algorithm? There is no like a single definition, but it's sort of like understood as an exact prescription defining a computational process leading from various initial data from to the desired result. So for any sets of initial data, you always make sure you get the desired result. And there are some common characteristics of any algorithm. So first of all, of course, as I mentioned before, it's discreteness. It means it consists of an ordered set of simple steps. And the steps are executed sequentially. You follow this sequence. It's also deterministic. So at each moment of time, the next step is uniquely determined by the state of the system. So this guarantees that for the same input data, you get the same desired result, right? It's contrasted with probabilistic. In probabilistic approaches, you have some probabilities. And it's not determined, you cannot guarantee that for the same input data, you have the same result. So clarity, so what it means? It means our interpreter, this programming language, you need to be in this syntax of the programming language. So it should understand your commands. You cannot just type, do whatever I want. So you need to use this particular lexica of that particular programming language and the functions that are defined there or in the library. So finiteness. So of course, it's very, very important property. Your algorithm should terminate at some point. It should not get stuck forever, right? It should halt after a finite number of steps. So some examples of like eternal loops. So you can have like while true, it's always true. We will discuss it later. So this is not a good option. So, and finally, universalism. It must be applicable to different sets of initial data. So you need to think about all these possibilities in terms of like input space, what the initial data might look like. So now a bit of an exercise for you. So it's testing your intuition now. You don't have to know this. So it's just your intuition. What do you think? Can all problems be solved algorithmically? In other words, can we design a general algorithm to determine from a description of any arbitrary program and some input data whether the program will terminate or not? Will it finalize or not? Or it will be stuck forever with this input data? So I will put it in the Speak Up forum for you. And did it work? Okay, so try to reach to this web.speakup.info and you go to this room and you will see the question. So I'll give you some time. I'll probably close it for now so you don't see the prior. So you are not biased towards what you see. So take your time. And while you're providing the answers, so let me just give you a little bit of history to address this question. So in order to address this question, we need to move back to ancient Greece. And think of ancient Greeks, whom I call Boolean geeks, because they just use lots of this Boolean logic in their reasoning. So they use the deductive reasoning. What means deductive reasoning? It's contrasted with inductive reasoning. So deductive, it means you start from general, you go to specific. And inductive, it means the opposite. You start with specifics and then you generalize. And they are, of course, famous for these syllogisms. Here's an example of a syllogism. All men are mortal. So there is a major premise. Socrates is a man, right? So it's a minor premise. So you have like this huge set of all mortal beings. Inside of this set, you have men that belong to this set as a subset, and then inside of man, you have this particular entity, Socrates, who is a man. So what can be concluded from that? So Socrates belongs to the set of men, and men belong to the set of mortal beings. So it means Socrates also belongs to this largest set of mortal beings. So we arrive to the conclusion that Socrates is mortal too. That's how syllogisms work. Okay, so before we do the next exercise, so we see that you're on the pessimistic side. Okay, so let's keep it in mind for now, and I will reveal the answer shortly. So, now let's do another practice. So let's try to play with the syllogisms and the reasoning. So now we have, let's call it question 1. So we have these different statements, and we need to evaluate whether the final statement is correct or wrong. So let's start with this first premise. Some of the snails are mountains. All mountains adore cats. Can we conclude that all snails adore cats? So let me put this as question 1. And question 1, and the number of choices. Again, we have 2 choices. So question 1, what do you think? So A is correct, B is incorrect. So there are some of the snails that are mountains. All mountains adore cats. Can we conclude that all snails adore cats? Yeah, of course we cannot do that, and you pretty much agree on this. So only some of the snails are mountains. Some snails are not mountains, so that's why not all snails adore cats. Okay, question 2. Let's go further with these exercises. So it's a bit trickier. Now you need to derive the conclusion by yourself. Flowers are green bees. Flowers drink vodka. What can we conclude from this? So there are options. A, all green bees drink vodka. B, all green bees are flowers. C, some green bees drink vodka. D, green bees do not drink vodka. E, green bees are not flowers. And F, all answers are incorrect. So let me put it as question 2. And how many? We have 6 answers. Oops, question 2 and 6 answers. Okay, the vast majority are correct. So it's the option C, some green bees drink vodka. Why? Because flowers are green bees. There are some green bees that are not flowers as well. So flowers drink vodka. It means that only some green bees drink vodka. That's how you derived. And Lewis Carroll, the author of the Alice's Adventures in Wonderland, was a logician. He was great in such logic puzzles, and he published a book in addition to the Alice's Adventures in Wonderland that is only on these like puzzles. Okay, now you can think that, okay, if we describe the world as this like sort of like this axioms, like set of axioms, and we also introduce the rules of logic, then we can pretty much explain the whole, everything, this logic of the world, everything about the world. Do you think it's true or not? So basically, paraphrasing this was the problem that was stated in 1928 as the Einschneidungsproblem. If you will read Cryptonomicon, it's well discussed there. So this Einschneidungsproblem asks basically, can we come up with an algorithm that considers as input a statement, like all flowers are green bees, and answers yes or no, true or false, whether this particular statement is provable using the set of axioms and the rules of logic. Suppose you describe all your world through these particular statements called axioms, and you introduced this full set of the rules of logic. Can you then evaluate any expression this way and explain the whole world? Okay, so let me just put it again on the Speak Up forum. I'll put it as Entscheidungsproblem. And we have only two options. Again, whether you're optimistic or pessimistic. So ancient Greeks believed that it's possible. Okay, so let's have a look. It's a lot more uncertainty here. We have higher perplexity now. So we have like more uniform distribution. So 56% are yes, and 44% are on the no side. So, and the answer to this is no. And this was proven as a part of Gödel incompleteness theorems in 1931. So the theorems state first that there is no consistent system of axioms whose theorems can be listed by effective procedures such as algorithm is capable of proving all truths about arithmetic of natural numbers. And the second one was the system cannot demonstrate its own consistency. In each such system, there are either axioms that you cannot evaluate. For instance, this statement is true or this statement is false. You cannot evaluate this statement. And there are also contradictory statements. And hence you have the logical paradoxes. And then it was also stated as any consistent formal system F within which a certain amount of elementary arithmetic can be carried out is incomplete, meaning there are statements of the language of F which can neither be proved nor disproved in this system. Using the axioms in the system, you cannot do anything about such statements. Again, this statement is false, is not provable at all. And then it was also proved mathematically by two independent researchers. One was Alan Turing, another one was Alan Church. So to prove this and to demonstrate that the answer to the Entscheidungsproblem is no, so Alan Turing introduced Turing machine and Alan Church introduced lambda calculus. And they worked independently. They used very different methodologies to prove the same thing. So the answer, so to reveal the answer, so the answer to the Entscheidungsproblem is no. And the answer to this earlier question, whether you can develop algorithm to evaluate any program, any initial input, whether it terminates or not, is also no, you cannot. There is no such algorithm. So you're on the pessimistic side. This is academia. You should get used to be on the pessimistic side. So, but one useful thing we need to remember from this is this wonderful Turing machine. It was introduced by Alan Turing in 1936, right before the Second World War. And it's a mathematical model. You know that there were no computers, right? We are all aware there were no computers at all. No idea of a computer. So it was a mathematical model of computation. An abstract machine that manipulated symbols on a strip of tape according to table of rules. So there is this machine, there is a like infinite memory tape with some cells, discrete cells. In each cell you have some symbols from some finite alphabet. For instance, it can be 0 or 1. So, and there are some rules here and the state, the internal state of the system. So this system is in the state 8, it reads the symbol 1, and then it looks in the table and decides in which state it goes next. So there is a table with states, the symbols that it reads, and there's rules. So this is this abstract idea of a computer. Again, at that time, there was no computer at all. So, and now let's turn to more practical side of the subject. So we already mentioned this simple program. And we mentioned that there are some discrete set of steps called statements. But if you look at this program closely, you can identify different types of that statements. Which statements do you think are qualitatively different from other states? So let's call this 1, 2, 3, 4, 5. So there are 5 steps, 5 statements. Which statements do you think are qualitatively different? Yes?
3 and 4.
Yeah, 3 and 4. In 3, we have this so-called loop. So it's keep taking the left turn. So we are repeating the same action over and over again until some condition is satisfied or something happens. And the number 4 is condition. So there is another condition. This is conditional statement. If you reach the beach, turn around and go back. So, and in our programs, we can identify the following building blocks. So simple statements, so it's like single comments to the computer. Sequence means we have some set of these statements, ordered set, of course. So a linear sequence of the statements. So control, so this is what we have as if condition. If something happens, then we do something. Or we do something only if something happens, right? So we specify this through if condition. Of course, we need to repeat some actions more than once sometimes. So for that, we do not just copy and paste print, 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 print. We just say for, so we use the loop, right? We put this particular statement inside of a loop, right? Copying and pasting multiple times is a bad practice. And of course, we want to reuse some parts of our code for different input data. We put these parts inside of a module or a function. So functions are blocks of code that can run with different inputs, right? So with, when you use loops, you just have the same setup. You have the same sort of like similar input, but functions, they kind of allow more variability. And finally, there are special types of functions that call themselves. They are called recursive functions or recursion. So now let's turn to Grok. So first of all, who managed to access Grok? How many of you? Raise your hand. Oh, there are still people who did not try. So first of all, if you want to access, you need to go through LMS through this assignments, right? So that, and you need to access the corresponding Grok worksheet from there if you're accessing it for the first time. So let me just quickly show you what do we have in Grok. Let's turn, so this is your Grok worksheet number 0. So in the Grok worksheet 0, you have just blockly those blocks of code. You don't have to write the code explicitly in Python. And you move it over here. And for instance, there is a particular building block that allows you to move a turtle. There's a special module called turtle. And we just have this turtle that is able to move in different directions, rotate, etc. And we can specify how many steps we need to move this particular turtle. So, and in order to run our small program, we just click run. Here it is. So this is our turtle, and we just moved it forward 100 steps. So this 100 steps is our input to this particular function called move forward. We can change it, so to 50 steps, run it. So, and your task in Grok, so you will have these circles with the description of a particular topic, and then you have diamonds. Once you finish, you get a green diamond. And your task is to get as many green diamonds as possible by the corresponding deadline. So you can also, for instance, you can move turtle 100 steps at a single instance, or you can just say, okay, 50 and 50. You can put together these building blocks, and it will be, the result will be the same as moving forward 100 steps, right? So just do this action 2 times. Okay, now let's move. By the way, in Grok, what is good about Grok is that you have this tutor messaging. So when you feel like you are stuck, you are not passing the hidden tests. This is typical scenario, and you don't have an idea what's wrong with your code. You just message tutors. It's very convenient, so the tutors can see what was happening in your code. They can see your code and the different time snapshots. And they can give you a hint. They will not give you an answer because it's examinable, but they will give you a hint what part of the code is not working well, and where to find search for a fix. Okay, so let's move. Let's move over here. So if we want our turtle to say draw an equilateral triangle. With the side size of 50. So what do we need to do? Can you give me just directions, what I need to put in? So our task is to make our turtle to draw equilateral triangle, right? So equilateral means the same side size, the same angles, right? So it's 60 degrees. A hint. So what do we need to do? And the length of each side should be 50. Yeah, so let's move forward 50. Then turn left 60. Then so let me just show you what happens. So this is our tiny start of triangle. Sorry? So change angle. Okay, 120. And now move forward. Okay, so move forward 50. So here it is. And now? Turn left, how many degrees? 120. And then move forward. So let's see. Hooray! Now, okay, so we are a bit running out of time, so I will very quickly. So try to practice this at home. There is another exercise to guess what this code will produce without providing this into Grok. So try first to run this code in your mind and guess what will happen. Okay? And so print functions you already mentioned a little bit with Shannon. So, and yeah, see you next week and enjoy the weekend.